In the 4th century, Aristotle came up with one of the earliest ideas of motion, proposing that an object needed a constant force to keep moving. Between the 6th and 14th centuries, scholars from the Islamic world and Europe developed the first concept of impetus, the idea that moving objects had an internal motion. It wasn't until the 16th and 17th centuries that Aristotle's initial idea of objects needing force to stay in motion was debunked by Galileo. Galileo argued that objects in fact did not need a force to stay in motion. This introduced the concept of momentum, which René Descartes expanded on by equating it to the product of mass and velocity. This discovery was later formalized by Isaac Newton in his second law, from which can be derived the formula for momentum, P equals mv. Newton's third law of motion provides reasoning for the idea that momentum in an isolated system is actually conserved. These laws together create our modern definition for momentum.
In our lab, we explored conservation of momentum through an elaborate and precise procedure. The purpose of this procedure was to see how fast a Nerf bullet would be going based on how high a pendulum swung.
The instruments we used in this experiment were
pennies, tape, Nerf gun and bullet,
paper towel,
plastic bottle, string, PVC pipe pendulum.
We made a pendulum stand out of PVC and tied 2 strings to it. We cut the top off a plastic water bottle, taped the other ends of the strings to it, and taped the pennies to the bottom of the water bottle. We then inserted a crumpled piece of paper and let the pendulum rest at the bottom of its arc. We prepped the Nerf gun and fired a bullet into the open end of the bottle.
To measure how high the bottle was displaced by the dart, we took a video of the dart hitting the bottle. We held up a ruler next to the bottle to measure the initial height, and then used the video we took to measure the final height when the bottle was at its highest.
And these were our measurements taken from the lab.
In this lab, we assume that the system is a perfectly inelastic collision. By Newton's third law, we know that momentum is conserved in an isolated system. So we can represent the initial and final momentums through this equation.
Treating the dart as m1 and the bottle as m2, we can say that m2 had an initial velocity of 0 since it was stationary before the collision. Doing some algebra, we can get the final velocity in terms of our known values. Then we can plug in the final velocity into the kinematic energy equation, resulting in this equation. This gives us the kinetic energy the instant the dart collides with the bottle. By the law of conservation of energy, the kinetic energy at this instant should equal gravitational potential energy at the peak of the bottle swing. Now we can isolate V1 initial to get the speed of the dart. By just plugging in our values, we get the speed of the Nerf dart.
Now, we made several early assumptions that have the potential to create error in our results. For example, we assumed negligible air resistance as well as a perfectly inelastic collision between the bullet and the cup, when in reality the bullet did bounce back from the cup somewhat. It's also likely that the pendulum did not swing entirely in one plane, and therefore not all of its measured energy was in the exact direction we measured it to be.
We found the initial speed of the Nerf bullet leaving the gun to be about 20 meters per second. When compared with the actual rated speed by Nerf of 21 meters per second, you can tell that our calculations were not far off. The fact that we were able to deduce this simply from the height that the pendulum had swung to shows us the inner workings of momentum, one of the most fundamental principles of our universe.